Sometimes it feels like chemistry has its own secret language, right? Well, today, we're going to crack the code. We're diving into organic chemistry, and I promise it's not just about boring diagrams. This is literally the language of life itself. And this explainer, think of it as your personal decoder ring. So, here's the plan. First, we'll get into the language of carbon itself. Then we'll figure out what's in a name. After that, we'll look at carbon's 3D shapes, check out some molecules with a cool twist, and finally, see how they all react. Let's get into it. All right, first things first. Before we dive deep, you gotta meet the main character of our whole story, the hydrocarbon. I mean, it sounds simple, right? It's just a compound made up of carbon and hydrogen atoms. But don't let that fool you. This humble little molecule is the backbone for literally millions of other compounds. Okay, so if we're gonna learn this language, we first need to know how to, read and write it. So how do chemists actually draw these molecules? Well, it turns out there's not just one right way. There are actually a few different methods to show the very same thing. Okay, check this out. Take a simple molecule, propane. The displayed formula is like the super detailed blueprint. It shows you every single atom and every single bond. No secrets there. Then you've got the structural formula, which is a little cleaner, a bit more compact. And then, my personal favorite, the skeletal formula. It's like the cool, slick shorthand that chemists use. That simple zigzag, every point and every end is a carbon atom, and you just assume the hydrogens are there. Super efficient. All right, so now you can draw it, but what do you call it? You can't just make up a name. We need a universal system, right? So that a chemist in Tokyo and a chemist in Toronto can talk about the same molecule and know exactly what they mean. And luckily, we have one. It's called IUPAC nomenclature. Let's look at butane. Its name is like a little story. The first part, bud, that's a code for 4. It tells you there are 4 carbon atoms all lined up. The second part, ane, tells you it's an alkane. And what's an alkane? It just means all the carbons are connected with single bonds. See? The name tells you how to build it. It's actually pretty logical when you break it down. And this is where the system gets really powerful. Watch this. We change just one little thing in the name. The ending goes from ane to ene. Boom. Just like that, you know everything's changed. That little switch tells you there's a carbon-carbon double bond in there now. It's not an alkane anymore. It's an alkene. The name literally gives away the molecule's personality and how it's going to behave. So you see, a name isn't just a label. No way, it's a complete instruction manual. If I say 3-bromobutanoic acid, and yeah, it sounds complicated, it's actually just a recipe. It tells you start with a 4-carbon chain, put a carboxylic acid on it, and then stick a bromine atom on the 3rd carbon. You could literally build the whole thing from scratch just by reading the name. Okay, let's move on. And this is a big one. Molecules are not flat. They are not 2D drawings. They're real, complex, 3-dimensional objects. And their shape is everything. I mean it. It's what determines if a drug will work, how our bodies get energy. Everything comes down to 3D shape. So what's the secret behind these shapes? It's a cool concept called hybridization. Here's how to think about it. Imagine carbon has a standard set of tools, its atomic orbitals. But for a very specific job, like forming a super strong bond, it doesn't just use one tool. It actually melts them down and forges a brand new custom tool, a hybrid orbital, that's perfectly designed for that one specific task. And you really only need to know 3 main types. If carbon is just making single bonds, like in alkanes, it uses what we call sp3 hybridization, and that gives you a classic tetrahedral shape. You see a double bond? That's sp2 hybridization, and the molecule flattens out. And if you have a triple bond, that's sp hybridization, and you get a perfectly straight line. The key takeaway here is simple. The type of bond dictates the shape. It's a direct link. The poster child for this is methane, CH4. It's got those 4 sp3 orbitals, and they all want to get as far away from each other as possible. So what shape do they make? A perfect tetrahedron. And this shape, this is not just some obscure geometry problem. It's the fundamental building block for so many things, from the fuel in their car to the fats in your body. Okay, get ready for a bit of a mind bender. What if you have 2 molecules and they are made of the exact same atoms? I mean, the same parts list, the same molecular formula, but they're totally different compounds. How is that possible? Well, my friends, you've just discovered the world of isomers. Think of it like this. Isomers have the exact same Lego bricks, but they're built into completely different models. And this isn't just a tiny academic difference. No, this can be a huge deal. One version, one isomer, could be a life-saving medicine, and its twin, made of the exact same atoms, could be totally useless or even dangerous. So, there are a few different types of isomers, but they all fall into two main camps. You have your structural isomers and your stereoisomers. And the way to tell them apart is to ask one simple question. Did you change the way the atoms are actually connected to each other, or did you just twist them around in 3D space? Here's the real gut check. For a structural isomer, think of a straight chain of carbons versus a branched one. To turn one into the other, you'd have to literally break bonds and reconnect the atoms differently. But for stereoisomers, the connections are all the same. The only difference is how they're arranged in space. It's like your hands. They're mirror images, right? But you can't stack your left hand perfectly on top of your right hand. That's what stereoisomers are like. And one really cool type of stereoisomer is called a geometrical isomer. So picture a carbon-carbon single bond. It's like an axle that can spin freely. But a double bond, that's totally different. It's rigid, it's locked, it can't rotate. And because of that, you can get two versions. One where the groups are on the same side, we call that cis, and one where they're on opposite sides, we call that trans. They're stuck like that, two completely separate molecules. All right, let's recap. We know how to draw them, we know how to name them, and we can even see them in 3D. So now it's time for the main event, the action. How do these molecules actually get down to business and react with each other? You know, every single organic reaction, big or small, starts with the same thing. A bond has to break. And there are really only two ways that can happen. You can have a nice, fair split where each atom gets one electron. We call that homolytic fission, and it creates these super reactive things called free radicals. Or you can have an unfair split. One atom gets greedy and takes both electrons. That's heterolytic fission, and it creates charged ions. So once that first bond breaks, it sets the stage for what comes next. And you start to see the same patterns over and over, kind of like classic moves in a chess game. You've got addition reactions where you're just adding stuff to a molecule. You've got substitution reactions where you swap one piece for another. It's all about recognizing these key plays. Let's look at one of these in action, free radical substitution. This is the definition of a chain reaction. It's like tipping over the first domino. It all gets kicked off by a bit of UV light. That's the initiation step. Then the propagation step is where the dominoes really start to fall. One radical makes another radical, which makes another, and it just keeps going and going. The only way to stop the whole cascade, the termination, is for two of those crazy reactive radicals to finally bump into each other. So when you put it all together, we've really started to crack the code, haven't we? We've learned the fundamental rules of this language, how to draw molecules, name them, see their shapes, and even guess how they'll react. This is the grammar that life itself uses to write everything, from a plastic bottle to the DNA inside your cells. We've unlocked the basics. So the only question left is, what are you going to decode next?